Welcome back to the Wellness Wisdom Podcast. Today we're going to be talking about physics and how it can impact the movement of everyday life. So basically, physics is how we move. And if we can understand some of the principles behind why we move and we can simplify it down, then you can take those principles, change them in your life, change them in the gym, and then, improve overall your movement system. So let's start with the basics of how we can move our joints. So the musculoskeletal system, which is muscle tissue, when it contracts, it pulls on bone through tendons. So when you hear somebody refer to a concentric movement, that means there is force generated in that muscle tissue, and that force is so great that it actually moves the bone. It shortens the muscle, which shortens the joint angle, causing a concentric shortening of that joint. So this contraction only involves muscle fibers in the resistance of the force. So if you could think about bringing a drink to your mouth, you are shortening those muscle fibers in your bicep muscle because you're stronger than that drink. In contrast, an eccentric movement would be the opposite. So when you lower the drink from your mouth to the table, your biceps will control that descent for you in that movement. So eccentrics can also be thought of as the downward phase of any exercise. So if you ever do pull-ups, the concentric would be pulling your chest to the bar, and the eccentric would be lowering yourself slowly. So during eccentric training, we can generate peak force. This is because we're using our muscle fibers, but we're also using that non-contractile tissue to resist the force, because gravity is pulling our joint and our muscle and lengthening it. And part of that resistance that we're able to provide against that eccentric movement is from our connective tissue. So this is why eccentric training, we're stronger eccentrically than concentrically. It's because we have more to resist with. An isometric movement you can simply think about as holding an air squat. So if you are doing a wall squat and you're holding a certain joint angle, so you're at 90 degrees, burning your quads, that is an isometric because there's no joint movement happening. However, the muscle is contracting. So how do our muscles perform all these movements? We're going to add layers of physics, beginning with what a lever is. So hopefully we've all interacted with a seesaw or a teeter-totter. And basically what it is, it's a fulcrum in the middle with two boards sticking out, and each person can sit on one end of the fulcrum, and if you sit with your legs off the ground, you are acting as a resistance arm, so your end will go down. However, if you kick up with your legs, you are creating a muscular force through that same lever arm. And the longer that lever arm is, the more your body weight will act as resistance, and the more your kicking will act as a force upward. So this idea is super important because it introduces mechanical advantage. So basically, the longer the lever arm is, the easier it is to generate torque. And so what torque is it allows you to manipulate objects by producing force and multiplying that by the moment arm, and that generates a rotational force. So that is to say, the longer the lever arm is, the easier it is to move things because you have larger amounts of torque. And mechanics know this implicitly, but we're just applying it to biomechanics, which is kind of like amazing actually if you think about it, because this is kind of a side note, but if you ever have you're doing car work or mechanic work and you have a bolt that is stuck, what do? You can buy these things called breaker bars, which are essentially just steel rods that will go over that wrench and multiply the amount of torque you have because that moment arm is larger. And why that's important is because our bones, our forearm, our legs, they're just lever arms for our muscles to act on, which, is pretty cool because we can change how these mechanics work. And as student physical therapist, that's what I do in the clinic. We're just manipulating moment arms to help people live their life. But a first class lever essentially is you have the resistance arm and the muscle force arm acting on opposite ends of the fulcrum. And these different classes of levers are, it's sort of how our body works, but depending on where the force is, like in a bicep curl, that's going to be a third class lever because it's differentiated because the resistance of the weight you're holding in your hand has a longer moment arm than your bicep muscle has its moment arm with the elbow joint. So a second class lever would be a calf raise. This is because that moment arm is in your favor, so you have a mechanical advantage because the calf muscle is on the back of your leg and the resistance or your body weight is actually going through the midfoot, which means you have a longer lever for which you can create torque. This is why a lot of people are very strong on their calves, hopefully, because of this mechanical advantage. A third class lever, as I said, the bicep curl, this is a mechanical disadvantage, and this is unfortunately how most joints in the body work. You have a longer resistance arm, and your muscles have to produce a larger factor of force to overcome that resistance because they're disadvantaged. And this unfortunately leads you to injury, especially if you think about your very tiny low back muscles when they're put in a position where they're in a curve and you're bent over, you're not braced. They have to withstand like 10 to 20 times the force that they're supposed to. That can obviously lead to strains, and we do not want that. We glanced over torque, longer lever arms, very easy for us to move things, and why that's important, well, sometimes we can't control it, right? So we were all born with this sort of biomechanical blueprint based on where our tendons were inserted. So if your tendons were placed far from the joint center, that allows you to generate more torque because that lever arm is longer for you. However, a longer lever arm means less maximum velocity and speed because the muscle needs to travel more distance to move the joint. So, pros and cons. This is why Olympians, if you look at different sports, like jockeys, less body weight, they're on the horses. Or basketball players, they're closer to the hoop, so they're usually taller. Those sort of anthropometrics show up everywhere. Muscle insertion is just one of them. Related is acceleration. So to understand acceleration, we must first talk about velocity. And velocity is essentially just meters per second. So when you're moving, you have a speed, you have a direction of movement, and acceleration is how fast that velocity changes, or the rate of change. This is also related to Newton's second law, force equals mass times acceleration. This is particularly important for athletes because speed is a key component of their work. So athletes who can command their mass at a higher acceleration rate have an immense advantage over slower opponents on in almost every sport. So if you can imagine like soccer, basketball, football, cutting, you want to be able to accelerate your force very quickly. And related to that is power. And power is essentially the rate that work is performed. And we know work is the product of force times displacement. So the concept of work can be used to basically quantify the volume of a lifting session. So you can measure the vertical distance a bar travels when you deadlift, and you find that displacement. And you can multiply that mass of the bar in kilograms of that weight by local gravity to find a force. And if you did 10 repetitions for 3 sets, you find that total volume for which you did that exercise that day. And this is important because if you're trying to tailor a program, you can get very minute progressions safely over time. So if you're just programming, you can consider the total volume of power or the total volume of work. And the concept of power is also important because to remain functional in society, you must be able to produce a certain amount of power. That's not necessarily true. There are people who get around, in power wheelchairs, but to cross the street, when you see that, that little man, the white blinking man, and you have to cross the street under a certain time constraint, you need an amount of power to perform work, and that work needs to be done quickly so you don't get hit by a car, right? And to find power, you basically just see how much work you can and then add in speed. So it's also important for a cyclist, and they can use wattage, which is their form of power, or heart rate to program their training so they can track their intensity level, essentially. And what's kind of controversial about power is that there is powerlifting, which has kind of corrupted the definition of power, because powerlifting, what do they do? So they're trying to lift as much weight as physically possible, and unfortunately, when you think about power, you think about speed, but powerlifters are usually not very speedy. So Olympic weightlifting is a higher amount of power because what they do is they're moving the bar with high velocity, high speed. The sport of powerlifting is low speed, high strength. So we'll get into that and kind of differentiate. But power is basically just work and displacement, the rate of work. And strength, on the other hand, is just simply the ability to exert force at any velocity. So the weight you can lift is usually, an archaic measure of how we measure strength. Recently, though, grip strength has been used to gauge strength in the literature, because if you think about what it takes to make a fist, your brain sends a signal to your hand, and that requires your nervous system. And strength is a proxy for how healthy that neural conduction system is. It's also a proxy for how atrophied your muscles are. So if you are, weak, it's going to show up in that isometric measure of grip strength. So this is important because grip strength has been shown to correlate very closely with mortality. So just simple things like strength can predict risk of death. So that's something we should be watching. But fortunately, strength is extremely modifiable, especially if we start early. So how can we change strength, or what are the components of strength? So as I was saying before, we have our nervous system. So there is a neural control component. So our nervous system uses action potentials, which are these little electrical signals, these pulses that we can use to recruit muscle fibers. And our ability to activate these muscles requires our mastery of this signal conduction. So interestingly enough, the first adaptation a novice lifter receives is in the form of motor learning or neural control. And this is because initially you're basically just learning how to contract your muscles, because I'm sure we can all remember, at least personally, when I was younger, I couldn't contract my abdominals, I couldn't contract my calf muscle, my pectoralis. You get the point. Any muscle requires a certain amount of mastery to contract. So that's similar in resistance and cardiovascular exercise because you're basically learning the best motor program to recruit those muscles. And this is why we get stronger super fast. They're called the newbie gains. And then after that, we get more advanced hypertrophy benefits the longer we do resistance exercise. So another way we can modulate strength is actually muscle fiber arrangement or pennation. And we can think of this basically as how are the muscle fibers feathered on their action or their insertion and origin. So some muscles are straight up and down. This is like your abdominal muscles. They're just stacked on top of each other. And the benefit of that arrangement is that you can contract it very quickly because the sarcomeres or the muscle fibers they're stacked on top of each other. You can think about your deltoid muscle, which has more pennation. It can produce more force like your quadricep muscles, because that pennation means that it's more feathered, so it can fit more sarcomeres or muscle fibers in a closer packed space. And this allows us to simply just make more force. And the benefit of the straight fiber arrangement, we remember, is faster contraction. More pennation is stronger contraction, simply due to density. Muscle length is something we can control because we can move our joints before we do something. So if you think about a muscle that is fully lengthened, you're going to have less mechanical advantage. But we're going to talk a little bit about the sliding filament theory. This is a huge concept that we're not necessarily going to uncompact today, but you can think about, hopefully you know what a sarcomere is. It's the basic fundamental unit of a muscle, and when it contracts, it can shorten because you have actin and myosin sliding over each other. And this happens because we have cross-bridge formation. We use ATP to shorten that muscle, and when the muscle length is fully lengthened, we have less potential to generate strength and force because there's less cross-bridge overlap. And we can think about this because the amount of force we can generate is exactly proportional to the number of cross bridges we can form at any given time. Meaning, the muscle length that is most conducive to producing strength is one that is in its resting length. So that's amazing for strength generation. We also have joint angle. So this is just re-saying the lever arm changes throughout the range of motion. We already know that. So if you can think about a bicep curl, when do you think that it would be the most difficult to do that movement? In a bicep curl, the movement arm is going to be strongest at 90 degrees. That's going to be where there is the most resistance against your muscles. So that's something we can control as well, because we can control the joint angle. But there's also contraction velocity we can think about. And this is basically just saying if you are to move the weight slower or faster, it can change how much force we can generate. This is because there's less time to generate cross bridges, to generate tension, when the range of motion velocity is slower. And one of the easiest things we can think about to increase strength is cross-sectional area, CSA. This is essentially if you were to take a circumferential measure of your bicep, that volume, that cross-sectional area of that muscle. Obviously you have fat and bone in there. However, if you could think about just taking a cross-section of muscle, what does that area look like? And a lot of this is trainable because we can hypertrophy or we can increase the size of our muscle fibers. However, some of us are taller than others, and this causes us to have longer muscle bellies, and unfortunately we do not increase linearly with our body size. So as we get taller, We produce the same strength if the CSA is the same. However, shorter athletes have a better command over their body weight than taller athletes because of this cross-sectional area. And this is seen in the strength to mass ratio. So when your body size increases, muscle volume and body weight increase proportionally more than cross-sectional area does. So this is to say we can control some factors and we cannot control other factors. That's why I think we should start first with the modifiable risk factors, the lifestyle factors that we can use to modify these, strength generation and interact in the world as best we can. So putting things into practice, how can you think about physics in a new light now? So when you go for a back squat, there's two ways to do it. Well, I guess there's more than two ways to do it, but I'm referencing a high bar or a low bar back squat. And you'll hear people talk about if you put the bar on your low back, a low bar back squat, that's going to emphasize what? Your glutes and your hamstrings. And why is that the case? Well, all of you know why now. Because when you're in a low bar back squat, your trunk flexes forward. That bar is closer to your knees, your knee joint. It's closer to your quads. And what's it further away from? It's further away from your glutes and your hamstrings. And this is causing a torque demand on those muscles. So this is to say, if you want to target your quad muscles, where are you going to put the bar? You're going to put the bar high up on your shoulders, because that's creating the torque demand on your quads, because the bar is further away from your knee joint. So when I figured that out, that pretty much blew my mind. So if you learned something, let me know in the comments, like, subscribe, and yeah, hope to see y'all in the next one. Peace.